Namaskar. Today we learn some terms those are related to electrical conductance and conductivity. First we study about the Ohm's law. According to the Ohm's law is given for the metallic conductors. According to the Ohm's law, when we pass a current through a conductor between the 2 points, the potential difference is directly proportional to the current flow through it. In mathematical formation, we can write Ohm's law like this. V is directly proportional to I. V mean potential difference, I mean electric current. When we eliminate this proportional sign, a constant is came there. That constant is known as R. R is known as the resistance. R is known as the resistance. That is the proportionality constant. So according to the Ohm's law, the equation is V is equals to IR. V is equals to IR. By this mean, what is the resistance? What is the resistance? The degree to which a substance prevents the flow of an electric current through it known as resistance. The property of a substance. The property of substance that oppose flow of electric current through it is known as the resistance. So resistance is the degree of opposition, the degree of opposite force that doesn't allow the flow of electric current. R is equals to, from the equation V equals to IR, the R is equals to V upon I. Unit of the R is ohms. Unit of the R is ohms. We also can represent resistance in a Greek letter by this symbol. This symbol, we pronounce it as a omega. So the unit of R is ohms or omega or volt per ampere. So the units of resistance is ohms or omega or volt per ampere. The most popular unit is ohms. Now the factors affecting electrical resistance. The factors affecting electrical resistance is the area of the cross section of wire. Resistance is inversely proportional to area of cross section. So R is directly proportional to 1 by A. It means if area of cross section is higher, then resistance is lower. Area of cross section is higher, then resistance is lower. Length of the conductor. Resistance is directly proportional to the length of conductor. R is directly proportional to L. More length, more resistance. More length, more resistance of wire. The material of the conductor. The material of the conductor by which we form a conductor. For like metals, wood, rubber, semiconductors, etc. For those, the value of resistance is different. The temperature of conducting material. The temperature, when we increase the temperature, generally what happens? Resistance decreases. But it is not true in the case of the metals. When we raise temperature, the metal's resistance is also increases. But in case of semiconductors and in case of non-metals, when we raise temperature, resistance decreases. So we can sum up by writing in a mathematical form that the R is directly proportional to L by A. R is directly proportional to L by A. When we remove this proportional sign, a constant is come there. That constant, we pronounce this as a rho. We pronounce it as a rho. So R is equals to rho into L by A, or The rho is known as resistivity or specific resistance. But nowadays we use the term resistivity instead of specific resistance. So rho is depends on nature of material and temperature. Rho is independent from the length, from the area of cross section, but the resistance is depends on length, temperature, area of cross section and the material. But the rho is depends only on temperature and material of conductor. The unit of the rho is ohm into meter or omega into meter or omega into centimeter. These are the units of rho. Rho is known as the resistivity. Whenever we talk about the metal conductors, we deal with resistance and resistivity. But when we deal with the solutions, liquid solutions, we use the terms conductance and conductivity. So the meaning of the conductance is the reciprocal or the inverse of resistance is known as conductance. The inverse of resistance is known as conductance. According to this, the mathematical formula of the conductance is G is equals to 1 upon R. R is known as the resistance and G is known as the conductance. So the unit of the conductance is ohm inverse or omega inverse, or SI unit of conductance is Siemens, that is represented by capital S. So like this, the conductivity of a solution. The conductivity is the inverse of resistivity. Conductivity is known as inverse of resistivity. Conductivity is represented with a Greek letter that is known as kappa. It is pronounced as a kappa. Kappa is known as the conductivity. So according to the definition, the formula for the conductivity is kappa is equals to 1 upon rho. Kappa is equals to 1 upon rho, or the rho, we place the value of the rho in this equation. On that time we got the kappa is equals to 1 upon R into L by A, and 1 upon R, we know that 1 upon R is known as the G. G mean conductance. So kappa is equals to G into L upon A. Kappa is equals to G into L upon A. Unit of kappa. The unit of the kappa is ohm inverse, meter inverse, or omega inverse, meter inverse, or Siemens meter inverse, or Siemens centimeter inverse. These are units of conductivity. Conductance of 1 ml of solution is known as conductivity. Conductance of 1 ml of the solution is known as conductivity. The value of the conductivity is depends on number of the ions those are present in a unit volume. Whenever we dilute a solution, the number of the ions no doubt increases, but the number of the ions in unit volume decreases. So the conductivity decreases by increasing dilution. We can understand this one with help of the example that we have in a beaker. We have ink solution. When we start to dilute that ink solution, the color of the solution will start to fade up. Why fade up? Because the number of the ink particles those are present in the unit volume decreases. So color start to fade. By this, we can easily conclude the conductivity is decreases by dilution of solution, because the number of the ions are decreases in a unit volume of solution. Now we compare the conductivity of some materials like conductor, insulator, and some compounds, chemical compounds. Look, conductivity of the conductors is very high. This indicate high value is indicating that these conductors are allowed to easy passage for the electron. easy passage for the electron, and the very low value of conductivity for the insulators is indicating that these particles or these material does not allow passing of the current. They have high hurdles for the electron movement. On the other hand, for the chemicals, look, the conductivity is fairly less, but that is highly greater than insulators, but very less than compared to metallic conductors. Like that, the conductivity of semiconductor is not too high, that is very low, but that is greater than insulator. That why semiconductors behave at the lower temperature like insulators, but at the higher temperature they behave like conductors. The magnitude of conductivity depends on the nature of material, temperature and pressure. Whenever we change the material or temperature or pressure, the value of conductivity changed. For the semiconductors, if we increase temperature, conductivity increases. We decrease the temperature, conductivity decreases. Certain materials like metals and their alloys, ceramic materials, mixed oxide, called the superconductors because their resistivity is almost zero. It means they have infinite conductivity. They have infinite conductivity. Thus material those have infinite conductivity is known as superconductors. It is known as a superconductors. Now the conductance through metal is called metallic or electronic conductance and is due to the movement of the electrons. The electronic conductance means the movement of the electron in a metal. That is depends on which factor. The first factor is the nature and structure of the metal. Second factor is the number of the valence electron per atom. More valence electrons per atom, more conductivity. More valence electrons per atom is indicating more conductivity. On the temperature, when we increase the temperature, conductivity of metals decreases. Why decreases? Because at the higher temperature, metal ions are start to vibrating and random zigzag movement of the electrons and metal ions. That random movement and zigzag movement of the particles is create a hurdle in the movement of free electron. Due to that, conductivity of the metals decreases. So when we increase temperature, conductivity of the metals decreases. As the electron enter at one end and go out through the other end, the composition of the metallic conductor remains unchanged for the years and years and the years. That is not depends that how much time we use that metallic conductors, because electrons are entering from one end and come out from the another end. So there is no change in the chemical composition of a metallic conductor. Now the conductance of electricity by ions present in the solution is called electrolytic or ionic conductance. Electrolytic conductance or ionic conductance. The conductivity of ionic solutions depends on the first factor is the nature of electrolyte added. The electrolyte is a strong electrolyte or a weak electrolyte. For the strong electrolyte, high conductivity. For the weak electrolyte, low conductivity. Because weak electrolyte generate less number of the ions, but strong electrolyte generate high number of the ions. The size of the ions produced and their solution. This is the second factor. Whenever the size of the ion is bigger, a big size ions does not move easily in solution. The small size ions can move easily in solution and faster. So the size of the ions is also affect conductivity. Their solution, how much those are soluble in that given solvent. So those are more soluble, more conductivity, less soluble, less conductivity. Next one is the nature of solvent and its viscosity. So our solvent is polar and non-polar. If that is the polar, how much polarity is there? So more polarity is there, more number of the ions can be generated. Next one is the viscosity. If our solvent is highly viscous solvent create a hurdle in the movement of electrons, in the movement of ions. Less viscous solvents give a smooth pass to ion and electrons. Next one is the concentration of the electrolyte. Higher concentration mean high number of the ions are present in a smaller region. So number of the ions is higher, but the area is very small. The volume is very low. So there is a hurdle between the movement of particles, between the movement and ions, because on that time your each ion is crowdy, that is covered by the large number of the ions, and every ion wants to move. So every ion creates a problem for the another one ion in the movement. Next one is the temperature. When we increase the temperature, whenever we increase the temperature, the bond between the electrolytes particle is broken down and the more number of the ions generated. More number of the ions, due to the high temperature, they have high amount of the kinetic energy, so they move faster. Those are moving faster, they increases conductivity of solution. Passage of direct current through the ionic solution over a prolonged period can lead to the change in its chemical composition. The change in the chemical composition by passing electric current through a solution. Why? Because the process of the electrolysis is start there. The process of electrolysis is start there. The process of the electrolysis converts your electrolyte in a simpler substance, simpler elements, in simpler compounds. Next one is the molar conductivity. Molar conductivity is the conducting power of all the ions. Those are present in the solution, and that solution is prepared by solvation of 1 mole of electrolyte. So a cumulative conducting power of all the ions, those are present in a solution that is prepared by 1 mole of electrolyte, is known as the molar conductivity. Another definition for the molar conductivity means that at a given concentration, the conductance of the electrolytic solution kept between the electrodes of a conductivity cell at unit distance. We place those electrodes far apart 1 meter or 1 centimeter at the unit distance, having the area of cross section large enough to accommodate V volume of the solution that contain 1 mole of the electrolyte, is known as molar conductivity. This definition say we prepare a solution by dissolving 1 mole of electrolyte in a solvent. The volume of the solution is capital V. We place this solution between the two electrodes, and the distance between two electrodes is 1 meter or 1 centimeter, and the area of the cross section of the electrode is large enough to accommodate that solution, so the conductance due to the all the ions those are present in that solution is known as molar conductivity. That is known as the molar conductivity. Molar conductivity is the property of an electrolyte solution that is mainly used in determining the efficiency of a given electrolyte in conducting electricity in a solution. So this is the efficiency factor. This also tells us about the efficiency of electrolyte for a given electrolyte. If we compare the two electrolytes of same concentration, if for one electrolyte molar conductivity is the high, for another one is the low, we can say the high conductivity electrolyte is more efficient in the term of that can generate more number of the ions, that can pass high amount of electricity. So we can compare the efficiency of two different type electrolytes. If the concentration is given in mole meter minus 3 or in mole centimeter minus 3 unit, on that time the formula we use for molar conductivity is lambda m is equals to kappa by c. This one is pronounced as lambda, not lambda. It is the lambda, not as a lambda. So pronunciation of this symbol is lambda. Lambda m is equals to kappa divided by c. If the concentration is given in mole per liter, the concentration is given in term of mole per liter, on that time we use the formula is molar conductivity is equals to lambda m is equals to kappa into 1000 divided by c. Lambda m is equals to kappa into 1000 divided by c. The unit of molar conductivity is Siemens meter square mole inverse. Siemens meter square mole inverse and or Siemens centimeter square mole inverse. So the units of molar conductivity is Siemens meter square mole inverse or Siemens centimeter square mole inverse. So we can derive this relation very easily that 1 Siemens meter square mole inverse is equals to 10 to the power 4 Siemens centimeter square mole inverse. We use this relationship for solving our numerical problems. So these units are very much helpful whenever we deal with numericals. Those are based on this concept of the molar conductivity, conductance and resistivity, resistance